let's now, so today the topic of the lecture is going to be localization. And actually localization is it's interesting. So this was first discovered for the Anderson. So I'll discuss mainly the Anderson model, and I'll give some results for other models at the end of the lecture. I hope today's, if not, we'll do it after the holidays. So this was actually the main discovery in the 58 paper by Anderson. And it was very surprising for the people at that time, and even for Anderson himself. And actually he wrote in, when they celebrated the 50th anniversary of this paper and of the discovery of localization, actually Anderson recalled that most of the people didn't believe it. Right? I mean, they found it very unnatural. So what's the problem? What's the idea? The idea is the following: is that if you take, for example, electrons, but it works for, it's actually a wave phenomenon, right? So it works for many waves, not only electronic waves, but it works also for sound waves, it works for light waves. It's really a phenomenon based on waves. And if you look at the Anderson model, so an electron which is moving inside a disordered system, so I actually, I can draw 1D, but right, and maybe 1D is the most astonishing, is that even if your electron moves at an energy, right, is at an energy E, which is above all these random barriers, right, take an energy E which is above the random barriers, then what happens is that the electron is going to be localized. So if I draw the eigenfunction, if I draw an eigenfunction associated to this energy, I'll draw it here. It's going to be localized, meaning that it's going to be L2 integrable. I draw something like this, because it's an eigenfunction. In blue. Value E. But imagine that E is above, so white is the potential, right? That's in white. But as E is above the potential, right? If you think of classical mechanics, okay, if you look at the equation for classical mechanics, so the potential is Hamiltonian is xi squared plus V of x, right? And so what you see is that for classical mechanics, P of x xi, at energies that high, it's going to move to infinity, right? It's going to slow down at some points, to speed up at others, right? But it's certainly going to move to infinity. Whereas in the quantum case, waves are going to be trapped, right? You don't need any hard walls, they are going to be trapped. And why are they going to be trapped? They're going to be trapped because of multiple reflection phenomena, right? What's going to happen is that for the classical mechanics, each of these bumps, right, is going, what's going to happen? It's going to, what is happening is that each of the bumps plays, actually each of the wells, rather said, plays as a part, plays the part of slowing down the particle, right? When the well gets deeper, right, when the wells gets higher, not the well, but when the bump gets higher, this is constant on the trajectory in the classical mechanical case, right? When V increases, it means that size has to be diminished. So the speeds, there is a slowdown in speed. But as soon as you pass the bump, you speed up again and go on, right? And because you're above, it never stops. But in the quantum case, what's going to happen, the fact that the electron is localized, is that the addition of all these slowing downs is going to lead to L2 decay of the eigenfunction. So the addition is, if you think in one dimension in terms of reflection and transmission coefficients, the addition of all these backward reflections is going to make your generalized eigenfunctions actually square integrable. Right? So it freezes the particle. Okay? And so And the funny thing is that this also happens, not at all energies, but it also happens in dimensions larger than 1, 2, 3, and in any dimension actually. Typically. It happens, not at all energies though, but at many energies. So what I'm going to write down is a number of theorems, and then we're going to prove them. Well, maybe not all the steps of the proof, but let's say the main steps of these theorems.
For non-random models.
Of course it happens for non-random models. I mean, the thing is, if you pick a sample in your random model, right, just one sample, for which this happens, it's a non-random model. I mean, the point is that when you prove this, right, you're going to prove that it happens for omega almost surely in some set of random operators, right? But you could look at exactly this random operator, I mean, not the random operator, but this sample of the random process, right? Which is not random anymore. Right? You see, it's just that random operators give you a framework where to prove this, right? Because they give you this big freedom in moving around the parameters where the same things roughly happen. But if you take an individual sample, it's just that you have a potential where this happens, right? Okay, so the random thing is really that you have a family where things happen for most of the members of the family, right, that behaves in a more or less homogeneous way, which enables you to analyze the family. But the single operator in this family is just any operator, right? So now you can ask what are really the properties that the potential should satisfy, right? What this tells you is that if it satisfies that it's the member of such a family, then this should hold true, right? But the fact of being a member of this family can be for just an operator which doesn't carry by itself a random structure, right? So what's the basic idea behind this? What is happening, right? What's the physical heuristics? What is the physical heuristics? That's the first thing I'm going to explain. So why do you expect that waves inside the potential, what people expected, I mean, they were surprised by localization, right? But why do you expect that waves inside the potential do not localize? But the basic idea is the following. Imagine that I take a small system, right, with a single well. So I take a small system with a single well, right, so let's say between 0 and little l, still one dimension, and I take an energy E here, which is corresponding to an eigenfunction, so I look at minus Laplacian plus V, I imagine that it's continuous, right, and I have an eigenfunction at energy E, let me say that 0 is here, that's the 0 energy level, negative, right, and we have an eigenfunction, phi, equals 0, right, and now I want to understand what happens if I take this level. So I imagine I have this level, this small potential, right? And I couple it. So here I have, for the moment, I have a Dirichlet barrier. I couple it to another potential, right? Which also has an energy level, let's say E prime. Here. Put 0. Yeah, 0 is not chosen exactly at random, right? It's because we're below the spectrum of Laplacian, but it's the simplest case. And equals E phi and minus Laplacian plus, so this is V prime. I first put Dirichlet here, right? Dirichlet. So I put Dirichlet always at the boundaries. V prime phi equals E prime phi. Right? And put a Dirichlet boundary condition. Now imagine that I remove the Dirichlet boundary condition. I remove the boundary condition. And I want to know roughly what happens, right, to the new system, which is made of these two potentials, but I remove the wall in between them. I let them interact. Okay? I let them interact. So, what's the easiest way to represent this? Well, if you do this, roughly, what you're doing is the following thing. You are having a 2x2 matrix, right? We just are looking at the low levels, below energy 0. Okay? So you're having one level at energy E, right, which corresponds to this. you have one level and energy E prime, right? And you have the fact that now, because you remove this barrier, you let the two systems interact. How do they interact? Roughly this level is, sorry, there's a prime here. This level corresponds to phi, right? This corresponds to phi. This corresponds to phi prime, right? So here you have some interaction term, which is corresponding to the, so here maybe I draw my, so here we have my phi prime, I draw it here, right? And here I have my phi. This is my phi prime, and so this is phi, and this is phi prime. Right? So imagine that the wells here are very deep. Right? Imagine that the wells are very deep. So we know, this is standard, we know that the phi prime is located, right? This is semi-classics. The phi prime is located near the values where the potentials inside the well, near the values where the potential takes values below E prime. Right? And here it's located here. And it's also known that the eigenvector is exponentially decaying when you get near, outside of this region, right? The eigenfunction, so phi, is exponentially decaying outside v of x less than e, right? And one actually can give the rate of decay and so on, right? At least if v is nicely behaved, right? So what do we have here? Here we have the following thing. We have the interaction between phi and phi prime is actually some number epsilon, where epsilon, right, is roughly, let me write in this one, e to the minus the distance separating, so I call this the well at E, and the well at E prime. So of course there are constant, it's, of course the true expression is more complicated than that, right? But roughly what you have is that you extend your phi, and here it goes on exponentially decaying, right? And what you get is something which is roughly an exponential minus some constant, the distance separating the two wells, right? And here you get, of course, the same epsilon. You have a symmetric matrix. And so if you want, this is equal up to a small error. Up to an error. This is equal to the operator minus Laplacian plus v prime restricted to phi prime, right? To the space, if you want, to the span, to c phi plus c phi prime. Right? If you span, you take the span of phi and phi prime, and you look at the matrix restricted to this, at the operator restricted to this vector space. Now, so we now have just a 2 by 2 matrix. Okay, so what's the spectrum of this 2 by 2 matrix? Well, it is well known that, so the spectrum 2 by 2 matrix, E prime, right? So what we can do is, of course, just we can assume, right? We can write this as E plus E prime over 2. Let's assume that, as in my picture, E prime is less than E. So this is E minus E prime. Also, let me call it. So I said E prime is less than E. So E minus E prime of 2. E plus, minus E prime over 2, epsilon. So this is the identity, right? This is where I don't write it. I just write a scalar. So this is, so we just are looking at a matrix. So here we have the identity. And when we're looking at the matrix, which is A epsilon minus A, right? And of course, by scaling, we can write this as, so we can write this if you want as, so we assume that, what is the best thing I can do? I'm going to rescale. So this is E plus E prime. I assume that E is different from E prime, right? Just to make. So it's 1 minus 1 epsilon divided by E minus E prime, or 2 epsilon divided by E minus E prime. All right, so I just want to know what is the spectrum of this, right? So, well, spectrum of this. This is equal to, I take the determinant of this, right? So I get x squared minus 1 minus epsilon tilde square, if I'm not mistaken. Maybe I should put, yep, minus epsilon tilde square, right? Let me check. So this is x squared. Sorry, minus x squared plus 1. Right, this is good. No, sorry, this is fine. This was fine. Ça fait x plus 1, x moins 1. Okay, and so we get as eigenvalues x equals plus minus 1 plus epsilon square, epsilon tilde square square root. Right? These are the eigenvalues. And what do the eigenvectors look like for this matrix? What do the eigenvectors look like for this matrix? Well, we solve, so these are x plus minus. One here. So we solve 1 minus x plus minus u plus epsilon tilde v equals 0, right? So we get what? We get, so u plus minus. So u plus minus and v plus minus are the components of the eigenvectors. So we get, which one do I take? I'm going to use x plus minus. So I'm going to get that, well, what do I take? I said that this is going to be minus epsilon tilde, and here I'm going to get 1 minus x plus minus. Right, so these are, I take non-normalized, just look at the shape, I take non-normalized, so if I look at the eigenvectors, the normalized eigenvectors, I get that phi plus minus look like 1 over epsilon tilde squared plus 1 minus x plus minus squared square root. And here I have minus epsilon tilde 1 minus x plus minus. Right? If I look at the eigenvectors, I have this, okay? And now, let's see what happens. So, let's see what happens in when epsilon tilde gets small. So I have, or big. Minus epsilon tilde. I'm going to replace here, sorry, this is this. And I'm going to replace this, so by 1 minus plus square root of 1 plus epsilon tilde, epsilon tilde squared, right? Okay, these are two things. So if epsilon tilde is much smaller than, so let me assume that epsilon tilde is positive, right? Let's assume that epsilon tilde is positive, is much smaller than 1. If epsilon tilde is much smaller than 1, right, then what do we get? Then we get that, what? Maybe I should have taken something. Okay, then we get that phi plus. Okay, so then x plus x minus are plus minus 1, right? So I get that phi minus. Phi minus is looking like What do I get here? Phi minus, so x minus is minus 1, right? So I get that this is looking like, well, 1 minus minus 1 is minus 1, and here we have, it looks like 0, 1, like this is roughly 0, 1, okay? And phi plus, well, it's going to look like, if epsilon is much less than 1, is going to look like, well, you have to do computation, but what's happening is that x plus, right, is going to 1. So it's going to look like epsilon squared. So we're going to have that this is going to be like epsilon tilde squared, right? Whereas this is going like epsilon. So it's going to look like 1, 0. Well, actually, the way I took it, it's minus 1, 0. Right? The ones I took, it's going to be like minus 1, 0. Okay, and what does it mean? It means that if epsilon is much smaller than 1, in the picture I have here, well, the new eigenfunctions, when you couple the two systems, are going still to leave one in this well and the other one in that well. But if epsilon is much larger than 1, right, what's going to happen is that then the leading term here is not going to be 1, it's going to be epsilon tilde, right? And what you see that phi minus is going to look like, I took here x minus, so I'm going to have minus 1, 1, 1 over square root of 2, and phi plus is going to look like minus 1, 1 minus 1, 1, 1 over square root of 2. Right? So in this case, the two eigenfunctions, the new ones, so here you have v prime, and the new eigenfunctions are still going to look like one of the eigenfunctions is here, and the other one, I draw it in blue just to make a difference, is going to look like this. Whereas in the new picture, you see that you're going to have, so in the new picture, you're going to have that one of the eigenfunction, this one is, this one, which is actually the bottom eigenfunction, is going to look like okay, and this one is going to look like this, right? And so you see that in this case, the two eigenfunctions get coupled. What does it mean? It means that actually here the two eigenfunctions are uncoupled. They essentially live apart from each other. What it means is that because of tunneling, in the second case, the eigenfunction got extended. It got extended from a single well, right, which is when you open the possibility to tunnel, it got extended from a single well to an eigenfunction that lives into the two wells, right? Okay, and what's the criterion? Of course, if epsilon is of order 1, it's going to be a mix between the two, right? You can check, you just write down the formulas, but it's going to be a mix between the two. And so what happens in general is that you should check. So if you have, imagine now that you have a random potential, the rule of thumb is the following. Imagine that I have an eigenfunction created by some part of the potential here. I have an eigenfunction created by another part of the potential here. What you should check is the tunneling coefficient. So this eigenfunction decays exponentially here, and this one decays exponentially there. You should check the tunneling. So phi 1, phi 2. Between the two, so you have two energies E1, E2. You should check the tunneling. So if e to the minus the distance well 1 to well 2, I have a constant something. Or tunneling, let me write it as this way. Tunneling between well 1 and well 2, if this is much smaller than the difference E2 minus E1, then the eigenfunction stay localized. And if the tunneling is larger, then the eigenfunctions delocalize. Right? So if you now think of a system of your random operator, think of the random operator, right? And I draw the picture in one dimension. So imagine you have a random operator, assume that the potential is non-negative, right? And that 0 is its minimum, right? That we have a potential made, for example, in the Anderson model, we have random variables that go down to 0. So you'll have portions in space, right? You have regions in space where the potential almost vanishes. And then you have smaller regions. Let me draw it in this way. Of course, the picture is not to scale. So you have regions in space where potential almost vanishes, right? Now, you remember when we did Lifshitz tails, we saw that to create low-lying eigenvalues, we need to have a rather large region where the potential is almost 0, right? So you have this large region. So let's say you have a region of size L, where the potential is almost 0, okay? And this will give you an eigenvalue. This region will give you roughly an eigenvalue of size 1 over L squared. Right? The eigenvalue is going to be of size 1 over L squared. Okay? Now, imagine that you want to find another region where the eigenvalue is of size 1 over L squared. You need to find another region that has a width, right, where the potential is almost 0, that has a width of size roughly L. Okay? What is the distance between two such regions? Well, it means that within this distance, right, if you call this distance L, you need to have two separate such regions, right? But this means that actually this distance L, so what does it mean? It means that you need to take two blocks, right? Each of them to have this has roughly a probability of occurring which is e to the minus L, right? And you have two independent such blocks in there, right? So it makes you a probability of occurring of roughly this size. Okay? And what you want to know is that this thing occurs with a good probability. So how many possibilities you have here, right? So that this occurs with a good probability. So I'm in dimension, I think of it in dimension 1, right? Otherwise the scaling is going to change. So roughly what you're going to have is that you're going to need, well, at least this probability, right, is going to be, if you, so let me think now. So one thing that is for sure, right? If I imagine that the random variables are given as in the Anderson model by at each point, right? Take a lattice here. At each point of lattice, you have an independent random variable, right? You need to choose at least. So you can, if you want to really have the configuration like this in blocks, okay? You can take all the pairs of blocks that can be built. Right? So a block like this is you have L over L, large L over little l blocks, and you want pairs, so the number of possibilities that you have is roughly this, divided by 2. L over L minus 1 over 2. Right? That's roughly the number of pairs of blocks of size L that you have inside this region of size large L. And you want this to be not too small. Say larger than epsilon. So it means that the distance, right? You want this distance not to be too small. So the distance, if you want this to be size epsilon, it means that large L needs to be larger than e to the minus constant times L, right? The constant, I mean the constant here and what is inside here, the constant that's not in here, needs to be, it depends on the epsilon you want. But if you want this to happen with a probability that's not negligible, you want something of this size, right?
F small.
Sorry, L small, yeah, definitely. L small, right? But then, okay, you want this to be, but then what is the tunneling? If the two blocks are at distance e to the minus L from each other, the tunneling is going to be e to the minus CL. Right, the tunneling, because it's e to the minus this, against there are constant in there, right? I forget about the constants, you just want the rough order. That's the tunneling. Tunneling is going to be this, right? But if the tunneling is this, what do we need to compare it to? We need to compare it, so we have size eigenvalues of this size. But the one thing we want is to see how close to each other these eigenvalues are. Right? But for this, we can use the Wegener estimate. Why? Because we know that on the block, this eigenvalue, right, is given by this block. So we know that the probability to eigenvalue, if you fix an, so you have a block here. You have another block which is far away. So the two are independent. Right? Two blocks are independent. So let's say you have B1 and B2. So the operator on B1 and H omega on B2 are independent. Right? These two are independent. And so, if you want to know how separated the eigenvalues are. So what you're going to say is that by Wegener, here we're going to use Wegener. It's not the only way to do it, but it's one way to do it. It's the simpler one. Well, you need a form of Wegener anyway. That's not, it's more technical matter. But by Wegener, you can say that the distance of H on the block 1, right, for any E inside H, in the spectrum of H on the block 2, the probability that the distance of E to H block 1 be less than, for example, I don't know, epsilon, right? This, we know that this probability is smaller than epsilon times the volume of the block 1. Right? So, the probability that there exists an eigenvalue in the spectrum of the block 1 and an eigenvalue in the spectrum of the block 2 such that they are at a distance from each other less than epsilon is certainly bounded by epsilon times the volume of the block 1 times the volume of the block 2. Right? Because for each eigenvalue in the volume of the block 2, these are independent by just the nature of the potential from the block 1. You can do this and you sum. You just sum. But this, imagine that epsilon is this. Block 1 and block 2 is the size of the blocks. I forgot the constant. Times L squared. Right? And so what does it tell you? This is much, much smaller than 1. So actually, it tells you that because of the random nature of the distribution, right, of your random variables, it is very unlikely that, at least at low energies, right, the eigenlevels of two far apart blocks be close enough together so as to kill, or so as to, interact or resonate with each other, right? So these eigenvalues actually should stay. Sorry, these. Well, here I'm exaggerating a little bit, right? Because what I should have used is something different. Okay, the reasoning is not completely correct that I'm doing here. I'll tell you why in a second. But nevertheless, so because we see the following reason is what you can say is that if L is of this size, you know that you know that the fact that you have two large blocks containing low-lying eigenvectors, right, is roughly of this size. So, but you could ask yourself, what's happening if I want the size L to be smaller? Then what happens is that I only have a small probability, right, that you have two blocks close to each other, right? The probability being given by this. Okay? And so what you should look at, the bad probability you should look at is actually the sum of this one and this one. Right? Because there are two bad configurations. Bad configurations are when they are close by blocks, right? Then this is one bad configuration, but we know that this happens only rarely because of this. And if there are far away blocks, the bad configuration is, do they resonate? Right? So we should look at the sum of the two. Right? The end estimate for a probability is not this, it's the sum of the two. So what you should do here is take something which may be not as large as this, or as large as this if you want, but change the C tilde, so that to get this one small, right? And then you have this one with a new constant, which is also small. So what you have, what you prove in this way is that with a good probability, right, there are no close by blocks, and far away from each other blocks essentially do not interact. Right? And that's the basic idea of localization. It means that eigenvalues that live in this block with a good probability, when you increase the size of the sample you look at, still go on living in the same block.
Is it in the exponent of L capital, E exponent of the plus CL, it should grow?
Oh, so yeah, sure, you're right, of course. Oh, it's a plus here, definitely. It's the same as here. Definitely. This is no, this is a typo, sure. Definitely, this should grow, and this is why you have a plus here, right? So you can allow such size and keep this still very very small. Okay, so change the constant maybe. And so this is the essence of localization, right? The fact that you have some, the idea is the following, is that if you want to create an eigenvalue locally, you need some special conditions. But if you want to find the same kind of conditions to create the same eigenvalue further away, you have to go really very far. So the two eigenvectors are going to be very small in the new place. Of course, this is not a proof, right? It's just heuristics. But that's the heuristics of localization. And so when you increase the size of the sample you're looking at, you incorporate more and more sites. What you prove is, well, you start with an initial eigenfunction. So roughly what you prove is that when you add the more and more sites, the shape of the eigenfunctions far away from where it started does not really change. Actually, the easiest way to prove it is not for eigenfunctions. The way it's done usually is through the resolvent. Right? What you show is that your resolvent has decay properties that stay the same when you increase the size of the cube over which you look at the resolvent. Right? Take a resolvent over a big cube, and then you increase it, right? And over larger cubes, the resolvent still keeps its nice decay properties. And of course, to go from one size of a cube to a larger size, you use the resolvent formulas in the type, the one I had written on the board when we proved the existence of the density of states, right? These geometric resolvent equalities. Okay, so that's the heuristics. So now let me give you the theorem that we're going to prove, and we're going to use actually a method which is due to, so this method, the method that goes along these lines is called multiscale analysis. Right? But we are going to use a method that was developed more recently. So this dates back actually to the mid-80s. So it was essentially developed. There was a paper, the groundbreaking paper is the paper by Frédéric and Spencer, 83. And it was refined by many people. And more or less, the most recent versions of it, the most recent and complete versions of it are due to Germinet and Klein. And this is in the early 2000s, so it's 2004 maybe. And they have some more work on it until 13, but they have a nice useful paper. So it's more or less it's presented as a black box where they tell you that you have some initial input estimates that you need to know, and once you have this, it gives you localization, right? But there is another method which was developed more recently, which is due to Eisenman and Molchanov, and this is 93, so 10 years later, and it was developed by Eisenman and collaborators later on. There are a number of papers, and this is due to a completely different idea, and this is what we're going to use to make the proof. So the method is not based on multi-scale analysis. It's more based on some harmonicity of the solutions of our finite difference equation. And the two methods have their own advantages. So this one is much more flexible, and it was adapted for many types of operators, actually for the Helmholtz equation, for elasticity equations, for wave equations, for many things. This one is actually more relying on the Laplacian, and it's, well, it was extended now to Schrödinger equations on the continuous, right? But it's less flexible, right? This one is much more flexible in a way, and it can be adapted easily to, in an easier way, to many other settings. Whereas the Eisenman-Molchanov method is a little bit more rigid, but it actually gives you better results. Okay, so localization for the Anderson model. Consider h omega lambda equals minus Laplacian plus lambda v omega, where what? On L2 ZD, where minus Laplacian is the one I wrote down, and v omega is just a matrix omega gamma delta gamma prime.
What message we will use?
We are going to use Eisenman-Molchanov, right? We're going to use Eisenman-Molchanov. Actually, it's shorter. It's in this case, it works very well. It's in this case, it's the preferred method. I mean, it's technically it's less involved, but it is in a way more mysterious. You'll see. Yeah, and we assume, to make it simple, omega gamma have bounded, compactly supported density. And that's not a restriction that can be lifted, but it makes things easier. So, well, the theorems are the following. Theorem. Theorem 1, actually I'm going to write a number of theorems. There exists lambda 0 positive such that for lambda larger than lambda 0, the spectrum of h omega lambda is equal to the pure point spectrum of h omega lambda. and the spectrum, the AC spectrum of H omega lambda, and the singular continuous spectrum of H omega lambda are empty. And this is omega almost surely. Right? That's the first thing. This is what is called Anderson localization, and moreover, there exists eta depending on lambda. There exists eta positive such that for E belonging to spectrum pure point, for E omega almost surely, if E is an eigenvalue of H omega lambda associated to what? Associated to let's say phi, then there exists C of omega and phi such that phi of gamma is bounded by by C omega phi e to the minus eta gamma. Right? So the eigenvalues, the eigenvectors decay exponentially.
And for what is the dimension?
Any dimension. This is for any dimension. This is why in dimension 1 you can remove this assumption. You can take for any lambda non-zero. Right? So remark. So if I put this lambda larger than lambda 0, right? Strictly. If d equal 1, one can take lambda 0 equals 0. Right? As soon as you have a random perturbation, you're going to have localized. Okay. So this is exponential decay. In dimension 1, you can actually say who gamma is, who the eta is. Right? You can. There's a dynamical systems interpretation of the eta in terms of the Lyapunov exponent of your operator. Right? But I won't speak about that. I mean, we don't need it. The second theorem I'm going to give is that, so this is theorem 1. Theorem 2. Actually, I will add one more part. So 1, you have this. 2. Maybe you can add it. I don't want to add 3. Just moreover, for lambda larger than lambda 0, the spectrum is almost surely simple. So actually there is a single eigenvector. I mean, there's a space, a subspace of dimension 1, right, associated to a given eigenvalue. Well, maybe I'll write the proof of this one too if we have time. Okay. Now that's theorem 1. So theorem 2, which is one of the results leading to theorem 1. Theorem 2. There exists lambda 0 positive such that for lambda larger than lambda 0 there exists eta positive such that what? Such that for any lambda inside ZD, a cube, lambda equals ZD possible. Cube. If you look at, I forgot the quantifier, let me think. Actually, the lambda eta positive I could put here, right? But oh well, it's fine. I think there exists eta, I'll put it here, and for any, I won't prove it for any alpha, but I think it's for, well, yeah, for any alpha in 0, 1. If you look at, so if we set G of E x y to be what? To be E minus H omega. So I take G lambda. So E H omega restricted to lambda For example, the boundary conditions that I've used up to now just project on lambda on both sides, right? Inverse, right? Take the kernel at x minus y. I look at the soup over epsilon positive of the expectation of g lambda e 0 x to the power alpha, and well, let me put the eta back in here. There exists, for any alpha, there exists, I don't want to compute what the eta is in terms of alpha. There exists eta positive, which is eta of alpha, e to the minus eta, I think it's 1/2 actually, maybe. Don't remember whether I can go 1 to 1, but eta to 1/2 I can go, that's for sure. Eta alpha modulus of, sorry, this times eta minus of x. I take the sum over gamma, sum over gamma in ZD. This is finite. So what did I do? I take the resolvent kernel, I take its alpha power, and I put an exponential increasing weight, and I sum over all the gammas. And this sum, right, this is a random variable. I take up, sorry, there's an epsilon missing, e plus I epsilon. So the resolvent is well defined because it's at a non-real energy, right? And I take the expectation of this, and I take the supremum, right, over E, and I can take actually the supremum over energies in real lines, right? And this is finite. So it means that for real energies, essentially, not the Green's function, right? Because when you are at an eigenvalue, this is going to blow up, right? This Green's function is certainly not going to be summable, right? It's the point value may well not even exist, okay? But what's happening is that if you take the average, it's going to exist. And moreover, so you see, because of Fubini's theorem, I could put the average inside here, right? I could take the sum and the exponential power and get it out of here. This is because by Fubini, this is the same as sorry. Right, that's the same as this, okay, just by, these are positive quantities. So this is the same as that, and so what I see is that these averages decay exponentially, right? So that's the second thing we're going to prove. So that's one of the parts of localization. Roughly from this, we will deduce pure point spectrum, right? And the next thing that we have is that theorem 3, which is called dynamical localization. Which is stronger than what one has here, is the following thing, is that under the same assumptions, there exists lambda 0 positive such that for lambda larger than lambda 0, there exists eta positive such that if you look at the kernel of e to the I t h omega, right? So you look at the quantum evolution of your operator at 0 and gamma, you multiply by e to the eta gamma of this, you take the expectation of this, well, you sum over the gammas, take the expectation of this, right? So this is the same thing. Yeah, I'll write it in this way. This is going to be finite. For sorry, I take lambda here, and I take the soup over the lambda in ZD, lambda boxes. Right? For any lambda, you're going to have this finite.
For what, t?
For any t, I'm sorry, I forgot to take the sup over t. Well, let me write it for any lambda in ZD. The sup over t real. Okay. Okay, so the three things more or less go together. And we are going to prove these things. I won't give the complete proof in the sense that during the proof I'm going to use general results on measure theory that I will not prove. But I give you references so for what I won't prove. Okay, so let's prove this. Yeah, now one thing I want to, so this tells you that, so it's not completely clear what's the relationship between these results, right? It's not completely clear. Here it's something about the eigenfunctions, okay? Here it's something about the resolvents, and here it's something about the Green's function, the evolution kernel, right? Well, you can go from the evolution kernel to the Green's function because of course I can multiply this by e to the ite, put the minus e here, and integrate in time, right? And get the resolvent out of there, right? On the other hand, you can go from this by integrating, and now if I want the phi of h of omega, if I want any function of the operator, I can just use the Fourier transform of the function and integrate the Fourier transform against this, which by Fourier's inversion formula will give me phi of the operator. Right, and use some L1, LP, LQ bounds and stuff like that to get estimates for the Fourier transform. Okay, if I want, imagine that I want to get something on phi of h omega lambda, I can write this, that this is just e to the it h omega lambda phi hat of t dt. Right, of course, as usual, I need to take a Fourier transform, 1 over 2 pi sitting over here. Right, this is just by the spectral theorem, right, and the Fourier inversion formula. So I don't remember, I think this is correct, but I don't remember exactly what the coefficient is, right? And the Fourier inversion formula, it depends what you put here. Okay, but I think 1 over 2 pi is correct. Right. Maybe it's 1 over square root of 2 pi. I don't remember, so there's a coefficient here.
Depends what is phi.
Exactly, it depends who phi hat is, exactly. But it depends who phi hat is, but once you've chosen this one, you want this one to be the inverse, so here the phi hat comes with e to the it xi, right? So phi hat of t here is roughly e to the minus it xi. Right, so here you have a coefficient, okay, that's fine, but it doesn't matter. Right, and so you see that you can go from now, if you want to have bounds on phi of h hat, you can use this, right? But when you have, so at least for phi's that are sufficiently regular, but once you have functions of the operator, you can use the functions and then the limit theorem to prove things on spectral projectors. Right, on, for example, you take phi equals spectral projector A to B, and then you use limit theorems to get something on the spectral projection on a single point, right, by letting this shrink. Okay, to enable you to get statements, right, from this on just the spectral projector corresponding to a single eigenvalue. Okay, so this way you can say things about eigenvalues. Okay, this is not exactly the way we're going to do it, but
from the resolvent we...
From the resolvent you can do the same kind of things, because from the resolvent using integration in complex, right, you can do the same kind of things, right? It's, again, it's not the way exactly it's going to be done, but you can try the same kind of tools. It's the usual thing, right? You have knowing you have, I mean, roughly here, what you're doing is you have a measure, right, that you are testing on a complete set of functions, and here you're testing it on another complete set of functions, right? And from this, you can extract enough information on the measure to know it, to know the measure itself, okay, completely. Okay. So, but I will not do all this, right? But so of course there is one difficulty though, right? Because the difficulty is the following. You see, the eigenvalues of this operator are random. They are random variables, okay? And here I take expectations. So I cannot just, for example, if I say something about something on the interval EAB, right? And I want to go to, by shrinking the interval to some value, right, E, what I need is that this value be an eigenvalue, right? But the problem is the eigenvalues are moving around. We've already seen that the probability that E be an eigenvalue is 0. So there's no chance you're going to do it. So there are some more subtle measurability issues, right? That you cannot perform the limits in just the brute way. Okay? So it's just to be, so you have to be a bit more clever than that. Right? Because the eigenvalues are moving around, I mean, quite fast. So, but the basic thing is the following. For the Anderson model, that's nice. Everything comes from rank 1 perturbation theory. So let's take an operator. Let's take it bounded as the Anderson-Hamiltonian is, right, as Laplacian is, and look at A of phi and take phi. So phi is a vector in the separated Hilbert space H, be A plus, well, let me call it not A of phi, but A alpha. So I just take a rank 1 perturbation of this. And alpha is a real parameter, so I assume that AB is self-adjoint. And I can, as I already said, I can compute the resolvent of A alpha from the resolvent of A by a simple formula. Right, this is a direct computation. It's 1 plus actually. Let me copy this correctly. Yep, that's correct. And here you have minus here. Okay, which you can also write as minus alpha as this. So that's direct computation, right? So you can set f alpha of z to be equal to a alpha minus z inverse phi right? And of course f0 of z, this we're going to write f of z is going to be f0 of z. So we set alpha equals 0, so this is 1 for A. And one has, directly from this formula, from star, f alpha of z is going to be equal to f of z 1 plus alpha f of z. Okay, now we did this for rank 1 operators, right? But if you think of the spectral measure of A, let me call d mu phi to be the spectral measure of A associated to phi. Then, of course, f of z is, if I put an alpha here, it's to A alpha and phi. Well, let me call it d mu alpha. So forget about phi. Phi is fixed. Then f alpha of z is nothing but d mu alpha of t minus z. Right? By definition. Okay. So actually, once you look at this function, okay, and you give yourself any measure, it doesn't need to be a spectral measure. Of course, any measure can be realized as a spectral measure, but if you take any measure, you can realize, okay, you can define f of alpha z by just this. So you can actually, this is actually something which is not operator theoretic, it's more measure theoretic, right? You can associate to any measure mu, which is a probability measure, so these are probability measures, right? I assume that phi has length 1. So these are probability measures. I can associate a new measure, mu alpha, by this perturbation formula. Right? And actually you can show that this gives you a measure, right? This bears the same kind of relationship. And so of course this measure is going to depend, it's given by the phi. Now, okay, the first thing we're going to do is what is called spectral averaging. And it is very much related to the Wegener's estimate, the way we proved it. So what is spectral averaging is just the following statement. One has a theorem or lemma. One has, if I take the integral of d over alpha, so I integrate the measure depending on the alpha parameter, I integrate this over alpha. Then this gives you a measure, and this measure is just the Lebesgue measure. Okay, so what does it mean? It means the following, right? This is just a short writing for any phi belonging to L1 of L1 d E, for example. If I do the integral of I integrate phi of E d mu alpha E d alpha, I get the integral of phi of E d E. Right, this is just another way of saying this. That is spectral averaging. So for theorem, let's prove this. By Stone-Weierstrass, I just need to do it I can do it for a first continuous function and then extend it, right, just by the usual thing. So I just need to do it for what? Let me think.
Resolver?
Yeah, the resolvent, but let me think. There's just one thing I have in. Yeah, I'm going to do it for the resolvent, that's for sure. I just have. Yeah, I'm going not for the resolvent actually, for something which is a resolvent shifted, right? The difference of two resolvents. I'm going to do it. I just need to do it. Prove for, let's say, f. Let me call it f of z and e. It cannot be resolvents because the resolvents are not integrable, right? But what I'm going to do, I'm going to do it. I'm going to what do I have? E here. So this is going to be E minus I, right? I just subtract so that this difference for e at infinity is going to be integral. So this is in L2, L1 of R for the Lebesgue measure, right? I need to extract this to subtract this at infinity. Okay, and now if I compute integral over R of what? Of f z e dE, right? Well, this is going to be 0 if, well, where do I have the pole? So here I put the pole at I, right? So this is going to be 0 if you have the imaginary part that is going to be on the same side, positive, and it's going to be 2 pi I if the imaginary part of z is negative. Let me put a plus here, so I invert this, so I keep the notations I have in my notes. E plus I, it changes the sides, right? It just changes the sides where you can shift to infinity and okay. And now if I compute integral over R of f of z e d mu alpha z d mu alpha e. Okay. What do I get? Well, by definition, I get that this is f of alpha at z minus f of alpha at I. Right? By the definition of mu alpha. It's just a spectral theorem. Right? And now I can use the formula I had here. So this is 1 plus alpha, sorry, this is 1 plus 1 over f of z minus 1 alpha plus 1 over f of I. Right, I just use this formula and divide the numerator and the denominator. Right. But what can I say of f of z and f of I? Well, for imaginary part of z positive, what do I know about f of z? I have that the imaginary part of f of z is positive, right? This is just because of the definition of f of z, right? This is a positive measure. This is because d mu alpha or d mu is positive. As d mu is positive, right? If I take the imaginary part, I get t minus z modulo squared, imaginary part of z, d mu, right? So I have this. Now the other thing. Okay. So of course, and if the imaginary part is negative, I have negative. Right? That's for sure. So now let's look. Here we have in alpha we have 2 poles. So this has 2 poles at minus 1 over f of I and minus 1 over f of z. Both poles are simple. Right? And the residues are the same. Right? Same residues, both poles, both simple. Same residue. Right? So if now I do the integral over alpha, right? So the integral. So let me call this I alpha of z. Thus the integral over R of I alpha of z d alpha. What is this? Well, it depends where the poles are. Right? So what do we know? Well, we know what the imaginary part, right? So this tells you that imaginary part of 1 over f of z is negative, and imaginary part of 1 over f of z is positive, right, in the first case. And in the second case, right? And so we know that this is equal to the two poles. So this one, 1 over f of z, minus 1 over f of z, sorry, has its imaginary part on the same side. If imaginary part of z is positive, right? So imaginary part of I is positive, so minus 1 over f of I has a positive imaginary part. Right? And so if imaginary part of z is positive, both poles have same sign for the imaginary part, so the thing is 0 if imaginary part of z is positive. And they have opposite sides of poles, right? And you look at the same residue, it's the residue that we had before, it's 2I pi if imaginary part of z negative. Which is, well, sorry, what happened? Oh, what happened here? Imaginary part of z. Did I make a mistake up there? If the imaginary part of z is positive, no, this shouldn't be 0, so it's interesting. So what do I say here? I have, this is correct, didn't change, no, there was no change in sign over there. This is correct. So I get that minus 1 over f of I. So if imaginary part of z is positive, then imaginary part of f of z, let me check this. This is also positive. So this one is negative. So this one is negative. Well, I don't understand why do I... So these have... Oops. Well, then they're on the, yeah, that's fine, then they're on the same side.
Yeah, but minus I maybe.
Well, thank you. That's it, I guess. Yeah, you're right. This is f of minus I. Thanks. Right. F of minus I. So, because this changes now. You're right. This is f of minus I because I have minus here. Thank you. This is what I was looking for. This is f of minus I. And so the imaginary part, so this one has the, it's on the other side in the complex plane. So this one, actually the imaginary part of this is here, it's negative, right? So they're both on the same side if imaginary part of z is negative, and they're on opposite sides of the real line if the imaginary part of z is positive. Okay, and we get the same result. Okay, so this proves what we needed to prove. Okay. Okay, and now, how late is it? Okay, it's almost finished, so yeah, I'll need next time. So I'm just, well, maybe we stop here for once. Actually, I'm going to stop on time for once. We'll stop here, and next time we're going to finish this proof, right? We'll finish the proof next time.